Hi, I'm Gonzalo Ron. I'm a partner sales solutions architect at AWS. And today we're going to talk about a topic I love, that is Earth observation. I really like this topic not only because it's super interesting from the tech side, but also because of the impact it has in our daily lives. Okay, so let's talk about our agenda for today. First, we are going to talk about what's happening on Earth observation today. We'll talk about some relevant topics like satellites, orbits, and the most popular use cases. Then we're going to talk about how to architect for Earth observation on AWS. I want to show you a typical architecture for an application that takes images from space, process them using a machine learning pipeline, and then show some results in a front-end application. So, my goal at the end of this session is that you have an idea about how to play with the available services, so you can start experimenting and building. Then, let's talk about the future of Earth observation. I want to show you why I'm so excited about this area and why you should be as well. So, the world is entering into what we call a new space age. Some people also call it Space 4.0. Let's see what has been happening. So, Space 1 is when humans started looking at the sky and started naming stars and constellations. It was the beginning of astronomy. Then, in Space 2.0, humans started competing between countries to dominate the space. The most clear example is the race between countries to reach the moon. Then, countries realized we have some problems on Earth and space that are bigger than any nation, and we started collaborating on the International Space Station. That's Space 3.0. We have thousands of experiments and a lot of collaboration happening there. What is amazing, right? Then we have what, in my opinion, is the most exciting stage, Space 4.0, or how some people call it New Space. In Space 4.0, space is no longer something for governments and big projects. Now we can see more and more the private sector investing into space initiatives. Space is becoming more reachable, and now we can see how space projects are mixing with other specialties like agriculture, insurance, and others. We'll talk about those use cases in a minute. So, as we can see, the space industry is growing very quickly. We're living a time where humans are placing robots to explore Mars. Humanity has a telescope in space that is trying to understand the earliest structures in the universe. That's just amazing. Also, we have an international space station that have done thousands of experiments and many countries collaborating. We're living a time where humans are starting going to explore space because of the private sector. So, space is no longer for people with very particular specialties. And even better, every year we're launching more and more satellites to space. And when we talk about observing our planets, satellites are very important for this conversation. So, how many satellites are out there? According to the United Nations, since inception in 1958, there has been more than 12,000 satellites in space. Just in 2020, more than 1,200 satellites were launched. That was a record at the highest number of satellites launches in a year. And in 2021, more than 1,800 satellites were launched, giving another record, with 41% increase of 2020. So, as you can see, there are more and more satellites in space. But why is this happening? As you can see in this chart, communications are the biggest contributor. Think about our mobile communications, TV broadcasts, and internet. Now we have those big satellite constellations that will provide internet to most of our planet. We'll talk about satellite constellations in a minute. The second biggest contributor is Earth observation. It's almost 30% of the pie. Earth observation, in this context, means taking images of our planet from those satellites and processing them to produce value. So, when I talk about Earth observation, people don't have any idea about the use cases. So, the first use case that is coming to their mind is, of course, weather prediction. Being able to detect extreme weather in minutes could save life, right? Another important use case is detection of oil spills. If that's happening, we want to know about it soon. Also, you can think about detection of pirate ships. For instance, if you are moving merchandise in the Pacific Ocean, let's say from Australia to South America, and there are a non-registered boat approaching to yours, you want to know about it quickly. Imagine taking pictures from space and detecting that problem in a matter of minutes. But please, don't think only about this particular use case. Let's think about tracking shipping in general. Another popular use case is agriculture. Think about water management and pest controls. The insurance industry is also using Earth observation. Let's say there is a natural disaster like an earthquake. It's far easier to take pictures from space to understand the damage than going into the place where the disaster happened. Some insurance companies are using Earth observation to speed up their claim processing. And an important use case is detecting bushfires. Think about what happened in Australia in early 2020. Taking pictures from space to identify bushfires and alert authorities can save lives. I love this use case, and we'll talk more about it in minutes. And just for more context, one of the reasons why Earth observation is getting more and more relevance is because of the development of a technology called radar. In very, very simple terms, with radar, instead of taking optical images, the antenna sends signals to our planet, and depending on the intensity and time taken to come back to the antenna, you can create the image. The advantage of this technology is that it's not depending on light. So, you can take images at day and you can take images at night. Also, you can take images in almost all weather conditions. That means you can literally see through clouds. And now that we are talking about bushfires, do you know how long it takes for a bushfire to reach what we call the megafire state? That's around 60 minutes. That's why detecting bushfires quickly is very important. After that megafire state, firefighters cannot do too much. Mostly, they have to focus on evacuating people. As you can see, low latency in fire detection and alerting authorities is extremely important. That's why I want to tell you about one of my favorite customer stories. EXI is a company that started as a university project. They could detect a very important wildfire in California after 66 seconds. Proving their hypothesis, they decided to go into market. EXI worked with AWS to create an automatic event-driven pipeline to store their images, process them, and alert authorities in less than 2 minutes. That's just amazing, right? For the tech people in the room, they scale their machine learning applications using Amazon EKS, so containers. They also use Amazon SNS to alert frontline responders, and use Amazon S3 to save the images. Now, we cannot talk about Earth observation if we don't talk about satellites and orbits. Now, I want to talk to you about a couple of satellites orbits that are very relevant for this conversation. And think about orbits like freeways, where satellites are traveling around our planet. The first one is low Earth orbits, or LEO. They have an altitude between 160 kilometers and 2,000 kilometers. For your reference, most of the commercial planes fly between 11 and 14 kilometers high. So even when LEO satellites are close to the planet, they are still very high. They produce a full trip around our planet in around 2 hours. So let's think about it. When you take a commercial flight from Australia to South America, normally it takes around 16 hours. So these satellites are moving very quickly, 2 hours in a full trip. So if you are curious, their speed is around 15,000 kilometers per hour. And they do around 11 orbits per day. They are great for weather forecasting, Earth imaging, and communications. A disadvantage is that they can only observe a fraction of the planet. This is because they are very close. As they are close to our planet, they produce images with great resolution. However, if you need to have persistent observation for a particular place in the planet, they are not good. Think about it. Let's say you want to monitor bushfires in a particular area of Australia. You take an image now, and as the satellite is moving very quickly, you need to wait for 2 hours to take the next image. How long did we say a megafire takes to form? 60 minutes. So you cannot wait for 2 hours to the satellite to come back. That's why a single satellite in LEO cannot solve what we call the persistent observation problem. So please keep this problem in mind. We'll keep talking about this in this presentation. Another kind of orbit that is relevant for this conversation are geosynchronous satellites. They are located on a very particular position above the equator, at an altitude of around 35,000 kilometers. Because of that very particular position, the satellite is rotating with the planet. So the satellite is always on top of the same position. They are great for communications and weather changes in a very particular location. Even better, As they are far away, 3 of them can cover the whole planet. Also, the antennas are cheaper because they don't have to keep tracking of the satellite positions. A disadvantage is that they are more expensive to maintain and the resolution of their images is not as good as in LEO. Of course, these satellites are far away. But let's come back to the persistent observation problem. These satellites are great because they are always on top of the same location. However, the resolution of the images is not great. You are far away. So, how could we keep persistent observation on a particular place of the planet? With LEO, you get great resolution, but the satellites are passing again every 2 hours. On the other hand, with geosynchronous satellites, you can always observe a particular place, but the resolution is not great. Some companies have tried to solve this problem using planes. For instance, if you have a plane always flying in a particular area. However, the logistics for this solution are hard. You need a pilot, and the pilot needs to rest. Also, you need to refill your tank. Another solution is drones. However, drones are highly regulated in many countries, so this is not really a solution. So what could be the solution for this problem? The solution is satellite constellations, and this is by far my favorite topic of this presentation. A satellite constellation is a set of satellites that work together as a system. We are talking about hundreds or even thousands of satellites working together to cover the whole planet. Satellite constellations are viable thanks to the development of something called autonomous flying. You know, space is a violent place, so we're not talking about satellites that are having a smooth orbit around our planet. Time to time, it's important to realign them. So, autonomous flying allows satellites to have some kind of self-awareness. So they are aware of their position and other satellite positions as well. Another important contributor for satellite constellations is the development of microsatellites. These satellites weigh less than 100 kilograms. And we even have nanosatellites that weigh less than 10 kilograms. So, go to the gym and try a 10 kilograms weight. You will see that's nothing, even if you have not been in at the gym for a while. So, as you can see, the persistent observation problem is solved using satellite constellations in LEO. In this way, you have persistent coverage and still great image resolutions. But I know, we have some technical people in the room that are eager to know how to implement Earth observation on AWS. So, let's see a typical architecture to bring your images from space, process them using a machine learning pipeline, and then make it available for a front-end application. My plan is to give you an idea about how to work with the key services so you can start playing with them today or tomorrow. First of all, you have a satellite that you are going to use to capture your images, right? You need it. Then you have 3 layers in your architecture. One to ingest your images, one to prepare your machine learning model, and one to use the model in real time by a front-end application. Just to set a use case, let's say you want to get your images from space to identify boats in the ocean. So you want to create a front-end application that will tell you if there are boats in a particular location of the planet. On the ingestion layer, you have AWS ground station. This service helps you to make your contacts to your satellites. You can onboard your satellite, and there are some satellites that you can use for testing. Then you can choose the satellite you want to use and the ground station for your contact. I mean, the AWS region you want to use. And the tool is smart. It helps you to choose from the times when the satellite is reachable by that particular ground station. Then you choose the Amazon S3 bucket where you want your images and wait for the moment of the contact. By the way, you could send your images to an EC2 instance as well. But I'll keep this example with an S3 bucket for simplicity. So you just have to wait for your images to arrive. So please try this. It's a fascinating experience when you are just waiting for the satellite to be on top of your region and you can see the images from space arriving into your S3 bucket. Then probably you want to create a machine learning model, so every time you receive a new image, you can identify if there is a boat there. To create this model, you can use Amazon SageMaker. This is a service that gives you the latest technology for machine learning, including Jupyter notebooks. In this way, you can train and visualize your machine learning models easily. So, to retrain your models, you can create a pipeline that uses the new images from the S3 bucket. Let's talk about that pipeline. You can use Amazon SageMaker Ground Truth to label your images and create your training datasets. Then, you can use Amazon SageMaker to create an endpoint that your application can use to validate if an image has votes or not. For real-time inference, to validate if an image has votes in real time, you can create a Lambda that reacts every time a new image is in the bucket. This Lambda can use Amazon SageMaker endpoint to validate if the image has a vote. Also, the Lambda can do other things. For instance, it can send a notification to the authorities, let's say an SMS, using Amazon SNS. Also, you can save some metadata into an Amazon DynamoDB table. The last part of the puzzle is creating a front-end application to access that data. If you are a front-end developer, please try AWS Amplify. It will help you to create your applications in the cloud quickly. You can use any of the most popular front-end frameworks for this. Your application could use that SageMaker endpoint or could go to a DynamoDB table to read the metadata for any image. I strongly recommend you to use these tools to work on your Earth observation projects. They can save you a lot of time. And now that we're talking about architecture, what should be the key considerations when you are architecting for Earth observation? The first one is defining your temporal resolution. Temporal resolution means the time between taking an image in a particular place and then revisiting that place for an update. For example, in the bushfire example, you need to alert authorities in a matter of minutes. So you cannot wait for hours before taking another image from the same place. You need to have a very good temporal resolution, probably a temporal resolution of minutes. Now, if you are working on an agricultural project and you are planning for pest controls, your temporal resolution doesn't have to be that good. For your temporal resolution, you have to ask yourself, do I need many satellites? How often should I schedule my satellite contacts? The other important consideration is your maximum latency. In the bushfire example, your whole process needs a very low latency. As soon as you get a new image, you want to notify authorities in a matter of minutes. On the other hand, for the agricultural example, you probably don't need that low latency. As you can see, low latency could be an important topic for Earth observation. And in some cases, managing this low latency takes a lot of computing power. And that's happening because you need to perform intensive, complex calculations at high speed. The obvious example is weather prediction, but there are other examples like researching our DNA and trying to find patterns to predict cancer. Another example is modeling to make commercial flights quicker. Some of these complex problems have not been solved because many companies feel constrained by the need of buying specialized hardware. That shouldn't be the case. Also, you want your people to be focused on developing your business application. You don't want them managing infrastructure. The solution to that problem is high-performance computing, or HPC. HPC is about using technology to solve the world's most complex problems at high speed. One of the most popular HPC solutions is the supercomputer. A supercomputer contains thousands of compute nodes that work together to complete a task. This is called parallel processing and allows you to complete those complex tasks quicker than ever. AWS has some solutions for HPC. Those solutions can help you to optimize your compute, network, and storage. But I want to give you a clear example. And there is no better way to show you this than a customer success story. And I love this one from Matchar. One of the things Matchar does is generating weather forecasts using HPC on AWS. They deliver Earth intelligence and space infrastructure, and currently they have more than 90 communication satellites in orbit and 5 robotic arms on Mars. The company is collecting data across more than 3 million square kilometers of satellite images per day. So, when there is extreme weather, you want to know as soon as you can, right? Minutes in advance can make a difference. For weather forecasting, Matchar started with around 230 EC2 instances to produce weather forecasting in 53 minutes. Please remember that number, 53. That was half of the 100 minutes taken by the weather supercomputer. But the team wanted to improve that time while reducing the cost. Then, using the latest AWS technologies, the team could reduce the time again to 42 minutes. that was a 22% decrease. Then they kept experimenting and reduced the time to less than 30 minutes. With that number, they use HPC on AWS to deliver weather forecasts 58% faster than the weather supercomputer. That is a crazy good achievement. Okay, we have been talking about what's happening on Earth observation. Now let's talk about the future. First of all, data and analytics will take more and more relevance. With satellites producing huge amounts of data, processing this data will help users to make smarter and quicker decisions. Machine learning will also take more relevance to identify patterns. Also, we're going to see space being combined with more and more specialties like shipping, agriculture, and others. And startups will keep booming at different levels. We have startups launching their own satellites, others creating insights from Earth images, others playing in the machine learning space, and even some companies are working on decommissioning of inactive satellites. So my message to you is that there have not been a better moment in history to work on the space industry than now. A quick call to action. Please try our satellite services, especially ground station. Again, it's fascinating when you prepare your setup for the first time and then you see the images coming from space into your S3 bucket. Really try it, please. Also, if you're interested in machine learning for your space project, try your machine learning services, in special Amazon SageMaker. In that way, you can access the latest machine learning technologies quickly. And as I say, please, don't feel constrained by your computing power. With your computer services, you have virtually unlimited power. And also try our storage services. I'm talking about S3 and all the different kind of databases that AWS can offer. You will see how you can save a huge amount of data at a low cost. You can see here some links in case you want to learn more about cloud computing. On the left, you have AWS Skills. That's an online learning center to develop your cloud skills. You will find training for anyone from beginners to experienced professionals. On the right, you can join the AWS certified community, where you can get recognition for your skills and you can be part of the community. I'll give you a second to scan the QR codes if you want. Well, thank you very much, and please feel free to reach out if you want to talk about Earth observation, a space project, or cloud computing in general. Also, we really value your feedback to help us improve our sessions, so please don't forget to fill the survey. Thank you very much.